For decades, one of Russia's most formidable military advantages was sheer geography. Missile assembly plants, command centers, fuel facilities, and heavy defense industries located hundreds or even thousands of kilometers away from the front lines were considered protected by geography itself. Distance functioned as an unyielding strategic shield. The vast size of Russia created a massive territorial buffer, allowing critical military infrastructure and industrial production to operate in total safety, far removed from the immediate danger of battlefield artillery and tactical strikes. That single assumption shaped strategic planning on both sides of the war for years. Russia operated on the firm belief that it could rely indefinitely on its vast industrial depth, churning out heavy armor, ammunition, and precision weapons without physical disruption. Meanwhile, constrained by capability limits and restrictions on foreign-supplied weaponry, Ukraine was forced to focus almost entirely on defending its cities, holding frontline trenches, and halting armored advances along the immediate line of contact. During the past year, however, a fundamentally new chapter has begun to emerge. Rapid advances in long-range uncrewed aerial vehicles, domestic missile production, and precision guidance systems have started directly challenging the long-held idea that distance alone can guarantee safety. The battlefield is no longer limited to front lines, mud, and trenches. It now extends deep into complex industrial networks, energy supply chains, power grids, and manufacturing centers that keep modern military forces operating. The question facing military planners is no longer only how to win tactical battles at the front, but how to systematically disrupt the broader industrial systems that keep those battles possible in the first place. Ukraine has steadily expanded its domestic long-range strike initiative, developing an entire generation of indigenous weapons designed, tested, and produced largely within its own defense industry. These include long-range attack drones and emerging missile platforms, created specifically to reduce total dependence on foreign-supplied weapons, while providing complete strategic freedom over when, where, and how these capabilities are deployed. For a nation engaged in a prolonged, high-intensity war of attrition, domestic production offers a massive strategic advantage. It drastically reduces vulnerability to sudden changes in foreign politics, international supply chain delays, or strict usage restrictions placed on imported weapon systems. Instead of relying entirely on outside support, Ukraine is actively attempting to build the self-sustaining industrial capacity required to generate and maintain its own long-range strike capabilities over time. Among the newest systems attracting intense international attention is the FP5 Flamingo cruise missile. Public information regarding the weapon remains strictly guarded for operational security, and several reported specifications have not yet been independently verified. However, official statements, defense disclosures, and publicly confirmed strike reports clearly indicate that Ukraine is investing heavily in long-range precision weapons engineered to destroy critical military and industrial targets deep behind enemy lines. Yet the significance of the Flamingo extends far beyond the physical missile itself. It represents a fundamental shift in modern warfare, where industrial capacity, rapid technological adaptation, software iteration, and the ability to manufacture weapons at scale become just as important as the military hardware already deployed on the front lines. Modern high-intensity wars are fought not only on the physical battlefield, but deep inside the factories, storage facilities, repair yards, and transportation networks that keep armies operational. Behind every missile salvo launched, every drone swarm deployed, and every armored vehicle repaired, on the front is a vast interconnected industrial system built on thousands of specialized parts and supply routes. A military's true strength depends on much more than the number of weapons or tanks it has available today. It depends heavily on the continuous ability to manufacture replacements, refurbish damaged equipment, move bulk supplies across vast distances, and keep specialized facilities operating under constant pressure. Destroying or disabling a single tank or launcher on the front line creates an immediate but localized effect. Damaging the core factories and energy nodes that supply those weapons creates compound systemic disruption that ripples through the entire military force over time. This is why military planners increasingly focus on the industrial foundation behind the fighting, targeting the supply chain and manufacturing nodes rather than only the front line itself. The objective is not simply to defeat enemy forces where they are actively fighting, but to weaken and choke the broader network that allows those forces to continue fighting week after week. Throughout the conflict, Ukraine has increasingly focused on striking targets that sustain Russia's long-term military operations, including heavy ammunition storage sites, oil refineries, aircraft repair facilities, and defense manufacturing centers. These operations are designed not only to cause immediate localized damage, but to force the adversary to disperse critical assets and divert valuable air defense systems away from the front line. Some of these deep strike operations rely on long-range attack drones, which can be produced rapidly in volume and launched in swarms to saturate defense radars. Other high-value missions reportedly involve domestically developed cruise missiles, giving commanders options for delivering larger warheads with higher speed and accuracy over huge distances. However, these deep strike initiatives must operate against one of the world's most heavily layered air defense networks. Russia has invested heavily in integrated multi-tiered systems engineered to detect, track, and intercept air threats before they reach high-value targets. This defensive architecture combines long-range surface-to-air missile systems, short-range point defense platforms, extensive radar coverage, and aggressive electronic warfare capabilities designed to jam GPS guidance and Seaver control links. The result is a relentless, fast-moving technological competition between offensive weapons and defensive systems. As long-range strike systems adapt to penetrate deeper into enemy airspace, defense operators continuously update their tracking algorithms, radar positions, and jamming tactics, driving an ongoing battle between missile design, low observable technologies, and electronic warfare. No air defense network, regardless of how advanced or multi-layered, can offer complete protection against every incoming threat. Modern air defenses are constantly challenged by low radar cross-sections, high speed, complex flight paths, and saturation tactics involving mixed swarms of drones and missiles. Low-flying cruise missiles pose an exceptionally difficult problem for ground-based air defenses because they can travel beneath conventional radar coverage for much of their flight. The natural curvature of the Earth limits ground radar detection ranges, while terrain features like hills, forests, and river valleys create blind spots that missiles can exploit. By hugging the terrain at low altitudes, these weapons minimize radar exposure, leaving defense crews with only minutes or seconds to detect, track, acquire, and engage the target before impact. Even so, flying low does not make a missile invincible. Modern air defense networks link ground sensors, airborne radar platforms, point defense cannons, and electronic warfare systems into a unified track network designed to maximize interception odds. Official strike reports from both sides frequently conflict. Defenders regularly report high interception rates, while attacking forces highlight successfully struck targets. Separating claims from reality requires looking past initial announcements. Successful strikes often generate dramatic visual evidence, dark smoke plumes, and global headlines, whereas intercepted missiles or failed strikes leave little visible trace and receive far less public attention. Building an accurate picture requires verifying satellite imagery, examining open-source intelligence, and carefully evaluating physical evidence on the ground. Understanding this distinction matters because the true military impact of a strike goes far beyond the initial explosion or satellite photo. A hit on a factory does not automatically mean production has permanently stopped. Facilities often operate with backup systems, alternative assembly sites, stockpiled components, or rapid structural repair teams that allow operations to resume surprisingly fast. The critical question is not just whether a target was physically hit, but whether that strike caused a lasting bottleneck in the adversary's ability to supply frontline forces. This inherent uncertainty is a defining feature of modern strategic warfare, where the real impact of an industrial strike may only become visible months later through shifts in battlefield supply, vehicle availability, or reduced artillery output. At the same time, both sides strictly manage the narrative surrounding long-range strikes. Governments selectively disclose details to demonstrate capability, maintain national morale, or influence foreign partners, while concealing operational losses or production delays. As a result, analyzing modern warfare requires evaluating multiple independent streams of evidence to determine where confirmed facts end and operational propaganda begins. The story of Ukraine's emerging long-range strike capability is therefore far larger than a single missile system like the Flamingo. It is a story about how global warfare is transforming in the 21st century. At its core, this is a lesson in rapid industrial adaptation, demonstrating how a country facing a massive military challenge can rebuild, adapt, and scale its defense industry while under active fire. It highlights how digital engineering, commercial technologies, rapid prototyping, and real-time battlefield feedback can be turned into strategic striking power under extreme pressure. It also raises a profound strategic question for military forces worldwide. Can a nation with fewer total resources challenge a larger opponent by developing affordable, scalable precision weapons that reach far beyond traditional front lines? For decades, long-range precision strike was the exclusive domain of a few wealthy nations with massive military budgets and highly specialized industrial bases. Today, the spread of accessible technologies, advanced navigation, commercial components, and rapid manufacturing is rapidly changing that balance of power. If long-range precision weapons become significantly cheaper and easier to produce in volume, the consequences will extend far beyond this single conflict. Nations around the world will be forced to rethink how they structure their military forces, protect critical infrastructure, and prepare for future high-intensity wars. The ultimate lesson emerging from this war may not be about one specific weapon or battlefield victory. It may be about a permanent transformation in the nature of conflict, where industrial resilience, rapid technological iteration, and the ability to adapt under fire matter just as much as traditional military power. And as defense planners worldwide study these events, one central question remains at the heart of modern strategy. In the future of warfare, will victory belong to the nation with the largest existing stockpiles, or to the nation that can develop, mass produce, and adapt its technology the fastest? The